And good morning to my fellow high altitude aerodynamics class, fall of 2019. If we are doing this presentation, we are just now starting into the cold season of the year, and I want to wish and thank every one of you a happy holiday season. This presentation is for our project as requested by Dr. Aaron Judy. My name is Prince Lala for the 4451 project presentation. The next slide shows us, this is the part 1 lift and coefficient of lift graph data. We have our degrees of pitch, the alpha range, which ranges from -15 to +21. Voltage, as explained by Dr. Judy to me, was the medium in which the air and the experiment was measured, right? Air has viscosity, it's a fluid, so they use the differential in voltage to convert then mathematically into lift and then coefficient of lift. The lift and coefficient of lift was understood and calculated by us, given the formulas by Dr. Judy. In here you can see that at -15 degrees of pitch, so when the nose is pitched down 15 degrees, there's only 0.04 degrees of 0.04. The coefficient of lift is 0.04, where the actual lift grade is -3.89, almost 4 degrees less than 0. As compared to when you come to the pitch of 18 to 20 degrees, almost 0.05 coefficient of lift, or 5 degrees. That's what I found it. Lift is 5 degrees here. The amount of lift increase is 5 at 21 degrees of pitch. That's quite a higher thing. And if you see it in a graph data, you can see how it passes, coefficient of lift passes right through 0 at 0.02. So knowing what I see here, I can say that this wing data, or this experiment, is for a subsonic wing and not for a supersonic wing, or it's not for a swept back wing. And the reason I say that is because it's a linear graph, and I don't see any of the swept wing quantities that we would see over here. The next graph is that of the data, and the data graph is also, so I can see total total drag here. This is for the drag part of it, say -15 to 21. Total drag goes in at the 3-degree mark of pitch to the 9-degree mark of pitch. We see a slight bump, and so I can predict that CL coefficient of lift and coefficient of drag, CL max, will be somewhere around the 7 or 8 degrees of drag to lift ratio, and I'll show that. And this is the total drag, which is our parasitic drag and induced drag totally, as graphed in the 3D graph. The next thing is lift and drag analysis that I did here. As I said earlier, at 3 degrees of pitch, the LD max is 0.001. At 9 degrees is 0.015. 6 is 0.09. So you can see at the 9-degree mark this is it. What I did was I subtracted in percentage 15 degrees of pitch positive to 15 degrees of pitch negative. It's 0.04, 0.04 here. It's 102 degrees difference between the lift created at -15 degrees of pitch, nose down 15 degrees or nose up 15 degrees. It's 102% different. Same thing for the drag. It's 108% difference. If I subtract, or if I add these two between the lift and the drag, I get an effective mean angle of attack, or LD max, of 7% difference, and that's what I see here. The next portion is I have two more. I just graphed our coefficient of lift versus coefficient of drag to show that the actual CL max would be right at 7.5 degrees, like I mentioned earlier. And then the same thing over here. This is lift versus drag. So the previous screen shows coefficient of lift versus coefficient of drag, 7.5% for the LD max. And then the next one shows again 7.5, but this is the lift versus the drag columns. And again, the same thing, lift and drag. So that is my presentation. Thank you for watching, and have a great rest of the holiday season. Thank you, guys. Leave some good comments. Let me know how I did. Bye-bye.